MATU 206, Week 7, Chapter 6. Rational numbers. Rational has a root word of ratio, and a ratio is a comparison of two values that look like a fraction. We have the real numbers, and the real numbers are divided into rational and irrational. Irrational numbers are anything that does not repeat and does not terminate, so non-terminating, non-repeating decimals. In other words, these are decimals that keep on going forever and ever and ever without repeating and or stopping. Rational numbers are made up of, the smallest group of them are the natural numbers, and those are the 1, 2, 3 counting numbers, like little children learn how to count. We have the whole numbers, which include the natural numbers and then add the 0. We have the integers, which include all the natural numbers, the whole numbers, and then also the opposites of the natural numbers, or the negative numbers. And then we have fractions, which are in a ratio. We have terminating decimals, meaning they stop, as in 3.75. It stops, so it's terminating. Or repeating decimals, which at some point will repeat, like 3.0555. The 5's repeating forever. That is a repeating decimal. So those are rational numbers, and yeah. Uses of rational numbers, we can use them for division problem. A rational number is really strictly a division problem, where that line in between says divided by. Hi, Sebastian. My cat just jumped up. So we have A divided by B. That's all a fraction is. So if we have this, what we really have is 1 divided by 2. So fractions really are just division problems. They can be used as a ratio, and we can even use them in probability to show them in a physical form. We have a possible whole. It's been divided up into 3 pieces, and we have one of those 3 pieces, so that is 1 to 3. We have a whole here that's divided up into 3 pieces, and then we have 2 of them, so we have 2 to 3, or 2/3. And here we have a set model where we have 5 objects possible, but we have 3 of them, so this shows 3/5. The meaning of a fraction. To understand the meaning of any fraction using the parts to whole model, we must consider each of the following. The whole being considered, and the whole is represented by the denominator. The whole shows the parts possible. The number of B-sized equal parts into which the whole is divided. The number A parts are the parts that we are selecting, or that we have, and that's what a fraction is. The number that we are selecting, or the portion, or that we have out of a possible whole part. So A to B, where A is less than or B, and well, it could be less than or equal to B, and greater than or equal to 0. And so we have 5 that we selected out of a possible 8, where we have the negative 2 out of a possible 3. Fractions, those are proper when the numerator is, I guess that's why it's less than B, because they're proper fractions. And we have improper fractions, where the numerator is larger than or equal to the denominator. So, for example, we have 8 out of a possible 5, the numerator is larger, or negative 3 out of a possible 2, the numerator is larger. They're improper. What numbers are represented on the number line? This is an example. Well, here's 0, and we can see that there's the whole number, or not the whole number, but the integer -1, and there's the integer -2. So each of these has been divided up into 1, 2, 3, 4 parts, and so this would be a -1 out of a possible 4. Here's the -1. Here is -4, 5. This is a negative because it's going in that way. 6 of these quarters, and so it's -6 quarters, but it reduces to -3 halves. Here's a -7 of these quarters, and so that doesn't reduce, so it's -7 fourths. Going this way, we have the whole number 1, and this has also been divided up into 4 possible pieces, and we have, at this point here, we have 3 of those possible 4 pieces. Here we have 7 of possible 4 pieces, and there's the whole number 2. Equivalent fractions are numbers that represent the same point on a number line. So we have 1 out of a possible 3, or 1/3. We have 2 out of a possible 6. That's 2/6. And here we have 1, 2, 3, 4 out of a possible 12. These are all equivalent because they all fall at the same place on the number line. If we have 0 and 1, and we divide it up into 3 sections, well, we would have 1/3 would be right there. So that's 1/3. But then if we chop them all up into 6 pieces, equal pieces, showing this one, then we have 1, 2 of them. That's at the same place. And if we chop all those in half, we have 12 possible pieces to make up the whole. 12 possible to make up the whole. This says we have 4 of them, which is 1, 2, 3, 4 of them, so it's there. They are all at the same place on the number line. So that makes them equivalent. Here's fraction strips, and this is kind of along the lines of some of the Singapore math ideas, which this book doesn't go into. And 1/3 equals 2/6 equals 4/12. We don't have thirds on here, but if we did, we would divide this up into 1, 2. I guess that's more like there. And that's 1/3, which is the same as 2/6, which is the same as 1, 2, 3, 4, 1, 2, 3, 4 twelfths. So you can show that with fraction strips also, just by taking a piece of paper, 4 that are the same length. One of them you cut in half, one of them you cut into 6 equal pieces, one of them you cut into 12 equal pieces, or divide it up, and you can show fractions. This is a good way for many students to see equivalencies. The fundamental law of fractions. Let a to b be any fraction and n a non-zero whole number, then a to b over b, or ab, is equal or equivalent to or the same as, if you multiply the numerator and the denominator both by n, you will still get an equivalent fraction. So finding a value for x such as 12/40 is equal to x 2/10. Well, I believe that 42 times 5 is 0 and 210. So what I did is I multiplied the 42 by 5. If I multiply the numerator 12 by 5 also, I find that x equals 60. So that means 12/42 has the same value as 60 210ths, because I can reduce them all to the same fraction also. But that's just saying that if you multiply the numerator and denominator by the same non-zero whole number, then you will get an equivalent fraction. This concept is very useful in the fact that we need to be able to do this in order to add or subtract fractions to find a common denominator. A rational number is in the simplest form, and so now we have to see about reducing these. So this a, I'm going to use prime factorization. 2 times 14 and 2 times 7, and 42 breaks down to 2 times 21, which is 3 times 7. I can cross out the common factors, so there's a 7 and a 7, a 2 and a 2, and I'm left with a 2 in the numerator and a 3 in the denominator. Then I have a breaks down to just a and 1, and a squared breaks down to a, and I can cross out a common factor, so I'm left with a 1 in the numerator, I'm left with an a in the denominator, or I can realize that I have a divided by a squared, and I can apply the exponent rules, where division says I subtract, and so that means I have a to the 1, which is this, minus 2, which gives me a to the negative first, but then to take care of the negative sign, I have to send that down to the denominator, which gives me a. And I have b squared divided by b squared, which just undoes each other, so I have 2 to 3 a's. B, so here I have a plus b times a plus b. That's what a plus b squared means. And I can factor out a common factor 3, so that's actually 3 times a plus b. And then since it's all division, I can have one of the a plus b's cancel each other out, and I'm left with a plus b divided by 3. This one also I can factor out an x from the numerator, so I have x times x plus 1 divided by x plus 1, which then undoes that, so I'm left with just x. If I were to know that a plus b times a minus b is the factorization of that, which is a squared, and I have a plus ab and a minus ab, which cancel each other out in the middle term, and then a minus b, I know that that's a plus b times a minus b, and a minus b can undo each other, so I know that I'm left with a plus b. I don't remember if this comes up later in this section or not, that squares, difference of squares. It's recognized that that's difference of squares, and that's why I knew that the factorization was a plus b, a minus b. Show that 12/42 is the same value as 10/35. Simplify both fractions of the same simplest form. That's method 1, which means I'm going to reduce. So I have 12 is 2 times 6, which is 2 times 3, and I have 42, which is 2 times 21, which is 3 times 7, and I can take out the common factors, and so that 12/42 I'm left with 2/7, and I can reduce 10 is 2 times 5, and 35 is 3 times, no, 5 times 7, and the 5's go away, and so that is also equal to 2/7. So by method 1 of reducing both of them to the lowest terms, I can show that they have the same value. Method 2, rewrite both fractions with the same least common denominator. Well, 42 I know breaks down to 2 times 21, and that's 3 times 7. 35 I know that that's 5 times 7. So 42 is 2 times 3 times 7. 35 is a 7 times a 5. So to find a common denominator, I have to multiply the fraction with 42 in it by 5, and I have to multiply the fraction with 35 in it by 2 times 3, which is 6. So that means I have 12/42 times 5/5. And notice I'm multiplying numerator and denominator by the same thing, so I'm going to have an equal value, which is 60 210ths, I believe, and I have 10/35 times 6/6. Again, I'm multiplying by 1, so I'm not changing the value, and that's also 60 210ths. So we can see that this method, they have the same value also, and rewrite with the same least common denominator, and rewrite both fractions with the common denominator. I really don't like this method because what we're just doing is we're not worrying about keeping it in reduced terms. So when the way to do this then is this butterfly or crisscross applesauce method. So I multiply numerator and denominator by 35. I multiply numerator and denominator by 42, and I get really big numbers that I end up working with. This is the fast and dirty way of doing this, but I resist showing students this because then they think that this is the easiest way of doing this, and they always default to this rather than method 1 or method 2. And they end up with working with really large numbers. Two fractions, a to the b and c to the d, where d is not 0, are equal only if and only if a times d is equal to b times c. Equality of fractions. The fractions are equal if this numerator times this denominator gives the same value as that numerator times that denominator. Ordering rational numbers, you can put them into order compared this way. If a, b, c, and d are integers, b is greater than 0, d is greater than 0, then a, b is greater than c, d if and only if a times d, and so this is finding out how to order rational numbers, is greater than b times c. What they're saying is if I have 1/2 and 2/3, I can find out which one's larger by taking this and doing 1 times 3, doing this 2 times 2, so I find 1 times 3 is that, and that is 4. I know then that 4 is greater than 3, so then I know that I can take that sign and put it in between there, and 2/3 is greater than 1/2. Denseness of rational numbers. Given rational numbers a, b, and c to d, there's another rational number between these two numbers. So there are always other values in between. Find two fractions between 7/18 and 1/2. Well, what I'm going to do is find that I'm multiplying numerator and denominator. So I have 7/18 and 9/18, and I can then see that 8/18 fits in between. If I need to, I can multiply this and get 14/36 and 18/36, and I can see that then there's 15/36, 16/36, and 17/36 in there. I can always just grow the fractions on either side and then find more values that go in between them. Addition of rational numbers. So 2/5 plus 1/5 equals 3/5. Since they have the same possible number, each of them has 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Same possible number of pieces to make up a whole. I can just add the parts. So there's 1, 2, and a third one makes 3/5. On a number line, I can show the same thing, that 2/5 plus 1/5 equals 3/5. And that's with a common denominator. So addition of rational numbers with like denominators. So if the denominators are the same, like meaning same, then you can just go ahead and add the numerators and keep the denominator. If we're going to add rational numbers with unlike denominators, first we need to figure out what the like denominator is. So the first step, in order to do this, we must find a like denominator and before we can add. So 2/15 plus 4/21. Before I do that, I need to know that 15 is made up of a 3 times a 5, and that 21 is made up of 3 times 7. So this is missing a 7, this is missing a 5. So the 15 fraction I have to multiply by 7/7. The 21 fraction I have to multiply by 5/5. And that gives me 14. 70 and 35 makes 105s, plus 20 105s is equal to 34 105. Here we have that negative 2/3 plus 1/5. A negative 3 is made up of a negative 1 times 3. A positive 5 is made up of a 1 times a 5. And what I really need to do, though, is multiply this one by 5, and this one has to be multiplied by a -1 times a 3 or a -3. So I have -3, -3. This one is 5 fifths. So that gives me 10 and 15s, and they're negative, plus a -3 15s. Signs are the same, so I have 13 15ths, and it's negative. Here I have 3/4 plus 1/5, which I have to add first because the parentheses say. 4 is made up of a 2 times a 2. 5 is made up of a 1 times a 5, so I have to multiply that by 5 and that by 2 times 2. So I have 5 fifths and 4 fourths. So that means 15 20ths plus 4 20ths. Which makes 19 20ths, and then to that I need to add 1/6. Well, 20 I know is made up of a 2 times 2 times 5. I have that right there. And 6 is made up of a 2 times 3. So that means the 19 20ths I have to multiply by 3. And this one I need to multiply by 10 tenths. So 60 makes 57 60ths plus 10 60ths, which makes 67 60ths, which is an improper fraction. I have no problem with leaving them improper. So the fraction x is made up of, and this is why I'm showing you especially finding common denominators with prime numbers, because all of a sudden we have a denominator of x, and that's made up of 1 times x. Y is made up of 1 times y. So what do I have to do? I have to multiply this one by y withs, and this one by x, which makes 3y over x times y, plus 4x over x times y, which means my common denominator is xy, and I have 3y plus 4x. Here, a squared times b is made up of an a times a b. A times b squared is made up of an a. I can line that one up. There's one b and another b, so what's missing here is a b, missing here is an a. So this one I have to multiply by bb's, and this one I have to multiply by a's. So that gives me 2b all over a squared b squared plus 3a all over a squared b squared, which my common denominator is a squared b squared, and I have 2b plus 3a in the numerator. Mixed numbers that are made up of an integer and a fractional part of an integer. So here I really have, and we call it 4 1/3. It really means 4 plus 1/3. So we can break things apart and work with them in that way. A mixed number is a rational number and therefore can always be written in the form AB. So how can I write this? I now have a common denominator of 1. But I need a common denominator. 1 is made up of a 1. 3 is made up of a 1 times a 3. What's missing is a 3. That means I need to multiply this fraction by 3/3, which gives me 12 thirds plus 1/3 equals 13 thirds. Now, in your elementary school days, you probably heard take the denominator, multiply it by the whole number, and add it to the numerator. 3 times 4 is 12 plus 1 is 13. That's what we're doing. That's just an algorithm that doesn't really lend itself to understanding. By splitting it up into 4 plus 1/3, making the 4 into an improper fraction of 4/1, and finding a common denominator hopefully shows a greater understanding of why this works as it does. And that's part of the Common Core is looking more at why instead of just how. Under the CST standards and stuff, we were really focused on how. Here's recipes, here's algorithms, this is how you do it. Although I've always been more interested in helping my students understand why, there was great importance put on how instead of why. So again here we have a -3 plus 2/5 Well, the whole thing's negative, so it's plus and negative. So I'm going to worry about that negative later. So I put in parentheses. I have a 1. 1 is made up of a 1. 5 is made up of a 5. So what's missing is a 5. So I have to multiply the numerator and denominator by 5. So that's going to be a negative. And then 3 times 5 is 15. And 5 plus 2/5 is equal to a negative 17 fifths. Oops, get rid of that extra 1 there. Negative 17 fifths. Here we have just 29 fifths. This is going the other way. We have an improper fraction. How do we get it? Well, remember, this line says divided by. It is a division problem. So the top goes in, 29, the bottom stays out. 5 into 29 goes 5 times. 5 times 5 is 25 with 4 divided by 5 left over. So that's 5 with 4 divided by 5 left over. That goes to the numerator. That stays in the denominator. Additive inverse property. For any rational number, there exists a unique rational number called the additive inverse such that if you add the two together, you will get 0. So the additive inverse property is just saying, what can I add to 5 such that my answer is 0? Well, that would be negative 5. What can I add to 2/3 such that my answer is 0? That would be a negative 2/3. Properties of the additive inverse are analogous. You go ahead and say that word. Analogous to those of the additive inverse for integers. So negative negative makes positive. Negative that makes and negative everything inside. Addition property of equality. If AB and CD are rational numbers such that AB equals CD, if they are the same, and if EF is any rational number, then if I add EF to this side of the equal sign and I add EF to that side of the equal sign, I still have an equal and equivalent value. So this is just the addition property of equality saying add the same amount to both sides of the equal sign and you haven't messed up the equality. Subtraction of rational numbers. If AB and CD are any rational numbers, then AB minus CD is a unique rational number EF, such that AB minus CD is equal to EF's. If AB and CD are any rational numbers, then AB minus CD is equal to AB plus the opposite of CD. And if A, B, and C, D are any rational numbers, then we can add, find a common denominator such that then we can put them together. And that's what this is doing, is just finding the common denominator. So 5/8 minus 1/4. In order to subtract, we have to have the same denominator. I know that 8 is made up of a 2 times 2 times 2, and 4 is made up of a 2 times a 2, so I'm missing a 2 there. Means I have to multiply this fraction by 2/2, so I have 5/8 minus 2/8 is equal to 3/8. And some of you are thinking, why are you going all that work? We just see that we can double 4 and get 8. I continually with my students go through these steps, even though I know it's easily visible, to see them and mentally do it, just to drill into them the process and the understanding of what it is we're doing rather than just shortcuts. Here I can split it up because I have 5 plus 1/3 minus 2 plus 3/4. And so I can really say that it's 5 minus 2 plus 1/3 minus 3/4. So I can split those up that way. Except for I see that 3/4 is larger, so I need to borrow one. So that's a 4, and I'm adding 3/3 to it, so I actually have 4/3. But then I have to have a common denominator, and my denominator is going to be 12. So I have to multiply this side by 4/4 and this side by 3/3. So I have 4 minus 2 is 2 plus 16/12 minus 9/12 makes 5/12. So I have 2 and 5/12, I believe. Let me know if I got that wrong. Here we don't really care about the numerator, but we do need a common denominator, and in order to add these fractions. So we're just saying it can be anything. Um, and 2 is made up of a 1 times a 2, 3 is made up of a 3, so I have to multiply um, this side by 3/3, and I need to multiply this side by 2/2, and so that makes 3x over 6 plus 2x over 6, and my denominator is 6, and 3x's plus 2x's makes 5x's. Okay, so here's more examples. 2 minus x over, and I hate saying over, but how else do you say this fraction? 6 minus 3x plus 4 minus 2x over 3x minus 6. They aren't the same, so first write each fraction in its simplest form. So 2x, what we can do is see that we can take out a common factor of 3, and so 2 minus x over 6 minus 3x becomes 2 minus x over 3 times 2 minus x, and then those undo each other, so we end up with leaving a 1 there, 1/3, and so this piece here comes into 1/3. Here we can take out a negative 2 in the numerator and a 3 in the denominator, and end up with an x minus 2. By taking out a negative 2, we leave with, because I'm flipping these around, okay. And those then go away, and we're left with a negative 2/3. And so what this really works out to be is 1/3 from the first part plus a negative 2/3. So 1/3 plus a negative 2/3 is really just 1/3 minus 2/3. And 1 minus 2 is a negative 1. So there's that answer. 2 over a plus b minus 2 over a minus b. Again, this is bringing in difference of squares. What we're going to do is multiply this side by a minus b over a minus b, and we're going to multiply this side by a plus b over a plus b. So that gives us 2 times a minus b. And well, then we can combine. Ugh. So that really gives us 2 times a minus b over a minus b times a plus b, and then there's that minus sign, and that gives us 2 times a plus b over a minus b times a plus b. And now that we have a common denominator, we can just use a minus b, a plus b as our denominator, and we have 2 times a minus b minus 2 times a plus b in the numerator. And then what we can do is use the distributive property, which they're showing here in this step, to get 2 times a minus 2 times b, and that's a minus 2 times a and a minus 2 times b. And then we can combine like terms in the numerator, and we have 2a, and a negative 2a goes away, so that leaves a negative 2b, and a negative 2b makes a negative 4b. And then we can use the not difference of squares. Oh yeah, it is difference of squares. And know that a times a is a squared, b times a negative b is a negative b squared, but an a times a negative b gives a negative ab, and a b times an a gives a positive ab, and that those two center terms cancel out, and so there's our final answer. Estimation with rational numbers. Many of the estimation and mental math techniques that are used with whole numbers also work with rational numbers. Estimation is an important role in judging the reasonableness of computations. So when we understand our problems, we plan our problems, we solve them, and then we look back. We can use estimation to find out if the answer we got is reasonable. A sixth-grade class is collecting cans to take to the recycling center. Becky's group brought the following amounts in pounds. About how many pounds does her group have all together? So they're saying use front-end estimation, which should be in the book, and adjust by using 0, 1/2, and 1 as reference points. So 1 1/8 makes about 1. 3 4/10, 4/10 is less than that, so that's about 3. 5 and 7/8, oh, but they're just using the front end. So it's 1 plus 3 plus 5 is 9. 4/10 is about a half. That's about 1. And so 1/2 plus 1. Oh, and 6/10 rather is about another half. So that's about 2. And so then 9 plus 2 is 11. So what's going on here is we're using the front end, 1 plus 3 plus 5, that's just the whole numbers to get an estimate. And then we're saying, oh, they'll throw that away. That's about a half. That's about 1. That's about a half. And put those together to get 2. So if we're going to estimate each of the following, 27/13 is about 2. 10/9 is about 1. And so I'm going to say estimate about 3. Here I'll use front end, and so 3 plus 2 equals 5. That's about 1. That's about 1. That's about 1. 1 plus 1 plus 1 is 3. 5 and 3 is about 8. Multiplication of rational numbers. Multiplication is repeated addition. It's just a fast way of adding. So 3 times 3/4 means we have 3/4 plus 3/4 plus 3/4, which means we have 3, 6, 9/4. And we can show that here. Multiplication is part of area. 3/5 times 1/2, so 3/5 times 1/2. We can take this 1/2 of 3/5 and we can show that that's the piece that's left, which will be just 3/10. So if A over B and C over D are rational numbers, then A over B times C over D, you just multiply straight across. If 5/6 of the population of a certain city college are graduates and 7/11 of the city's college graduates are female, what fraction of the population of that city is female college graduates? With so many ofs in there, it really leads me to believe I'm going to be multiplying, because that's a clue word for multiplying. So I want to know 5/6 of 7/11, which makes 5/6 times 7/11. I can't do any cross canceling or reducing. Can't reduce up and down or across the corners. And so 5 times 7 is 35, and 6 times 11 is 66. Multiplicative identity again. What number can I multiply a fraction by or any value by and not change the value? And that is 1. The additive identity, remember, is 0. The multiplicative identity is 1. Multiplicative inverse is for any non-zero is the unique rational number such that when you multiply, what can I get will give me 1. So what can I multiply 3/5 by? Multiply such that I'll get 1, and now I multiply by the inverse of the fraction, because then we can cross reduce there and end up with 1. Distributive property means I'm taking this value outside, which is a multiplication, and multiplying it across the addition in there. Multiplication property of equality. If I multiply both sides by the same value, I don't change the equality. That's what that's saying. Multiplication property of inequality. Same thing. If I multiply the same value, both sides of the inequality sign, I don't mess up the inequality. And multiplication property of 0. Anything you multiply by 0 is 0. A bicycle is on sale at 3/4 of its original price. If the sale price is $330, what was the original price? So X is the original price, but 3/4 of X will be the sale price, because 3/4 of the original price. We multiply both sides by 4/3 to isolate X, and we end up with let's see, 330 times 4 is 12, 12, 13. 1320 divided by 3, so that's 1320 divided by 3. We can do the division. The top goes in, bottom stays out. The original price of the bike then is $440. Multiplication with mixed numbers using improper fractions. This is the way I tend to do it. You change the improper fraction or the mixed numbers into improper fractions, then you can multiply straight across and reduce. Or you could do distributive property, and this tends to get confusing for students, so I really don't recommend that process. Most of them will come in knowing this. Division of rational numbers, how many halves are in 3 wholes. Here's a mistake that many elementary teachers make that say when you divide, you'll get a smaller number. And I've gotten into arguments with some of my middle school students as saying that but you divide, you need to get a smaller number. My teacher in 3rd grade or 4th grade told me that. It's not true. If you divide by a number greater than 1, your number greater than 1, then yeah, you'll get a smaller number. But if you divide by a number that's less than 1, you don't. So 3 divided by 1/2 is actually equal to 6, because you take the 3 wholes and chop them into 1/2 and you get 6 of them. How many 8ths are in 3/4? That means 3/4 divided by 1/8. If you take a bunch of 3/4 and you chop them up into 8ths, you'll end up with 6 of them also. How many 3/4 are in 7/8? And so what we can do is we can find 7/8, and we can chop that up into 3/4 pieces. So there's 1/4, 2/4, 3/4. There's just is made up of 6 equal sized pieces of length 1/8. And so you would get 1. There's the 1/3, and whatever fourth that part is left over, that's 1/6. So you have 1 1/6. I guess I want to. What most people will say is when you're 7/8 divided by 3/4 is that you invert the divisor and multiply. So 7/8 times 4/3, and then we can reduce across there. 4 goes into 4 one time, goes into 8s, which makes 7/6, which is that answer there. So that's the mathematical way of doing it. Why are we doing this? Why are we able to? I don't want to divide by a fraction. I'd rather divide by 1. So if I have 7/8 divided by 3/4 and I want to divide by 1, is there a way I can change that 3/4 into 1? Yes, there is. I can multiply by its inverse, if you remember that property a while back. But if I multiply the right side, I also have to multiply the left side, and that makes which makes 7/6 divided by 1, and divided by 1 just goes away. So really, by multiplying both sides, by making that divisor into 1, I'm inverting and multiplying, and that's why that works. If a, b, and cd are any rational numbers that c divided by d is not 0, then ab divided by cd equals ef. If and only if ef is a unique rational number such that then when I take that and multiply it back by the divisor, I get the dividend. When two fractions with the same denominator are divided, the result can be obtained by dividing the numerator of the first fraction by the numerator of the second. To divide fractions with different denominators, we rename the fractions so the denominators are equal. We're finding the same denominator in order to really divide them. Radio station provides 36 minutes for public service announcements for every 24 hours of broadcasting. So what we're doing is looking at how many minutes per hour, what part of the broadcasting day is what part or what fraction of the broadcasting day is allotted to public service announcements? Well, we have minutes and we have hours. So one of the first things we have to do is convert hours to minutes. 60 times 24, because there's 60 minutes in every hour, makes 1440 minutes in a day. So we have 36 minutes out of every 1,440 minutes, or every 24-hour period. When we reduce that, that gives us 1/40th. How many 3/4 minutes public service announcements can be allowed in 36 minutes? And so it's saying, if we have 36 minutes, how can I divide that up into 3/4 minutes periods? And again, I don't want to multiply or divide by a fraction. Dividing by 1 is much easier. I can change this side into 1 by multiplying by the reciprocal. If I'm going to multiply that side by the reciprocal, I have to multiply this side by the reciprocal. This is going to go away and leave 36 times 4/3, which means I can reduce across there, and that makes 12, and 4 times 12 is 48. We have 35.5 yards of material available to make towels. So we have a big long piece of cloth, 35.5 yards. And each towel requires 3/8 of 1 yard. So what we're saying is we're chopping that up, each yard, into 8 pieces, and we need 3 of them to make a towel. How many towels can be made? And so 35.5 makes 71 halves, divided by 3/8. I don't want to divide by a fraction, so I'd rather divide by 1, so I can multiply that side by its reciprocal, which means I have to multiply this side by the reciprocal. This then becomes divided by 1, so we can throw that away. 2 goes in there, 1, and that's 4. 7 plus 1 is 8, so that isn't divisible by 3, so that won't work. And so 4 times 71 makes 284 thirds, and then that reduces to that. But since it's how many towels, we have to throw away the 2/3. How much material will be left over? Because the division was by 3/8, we have 2/3 of 3/8 of is a clue word for multiplication, and so that becomes 1, and that becomes 4, and that's 1 and 1, so we have 1/4 yard left over. A bookstore has a shelf that's 37.5 inches long, 37.5 inches. Each book has placed on it is 1 1/4 inches wide or thick. How many books can be placed? So we have 37.5 chopped up into 1 1/4. So we need to change these to improper fractions. So 2 times 37 makes 74, 75 halves. Did I do that right? 37 times 2 makes 14. 74 plus 1 is 75. Divided by 5/4. I don't want to divide by a fraction, so I'm going to multiply this side by its reciprocal so I can divide by 1. And that means I have to multiply this side by the reciprocal also, or invert and multiply. That goes away. That becomes 1, that becomes 2, that becomes 1, and that becomes 15, which means there are 30 books that can fit on the shelf. Estimation and mental math with rational numbers. Same strategies can be used. Estimate each of the following. That's about 3, that's about 8. 3 times 8 is about 24. This is about 25, and that's about 4. 25 can get chopped up into 4. 6 times about. Extending the notion of exponents. So a to the m means we have a times itself, a, the base, m times. And so a to the m is just a times itself that many times. A to the m times a to the n, This is a product with the same base, so it's a product of powers. And a product of powers, you just add the exponents. So if I have 4 to the third power and I want to multiply that by the same base, 4 to the fourth, really what I have is 4 times 4 times 4 times 4 times 4 times 4 times 4, or I still have the same base 4, but now it's 1, 2, 3, 4, 5, 6, 7 to the seventh. I just add the exponents. Uh, any value to the 0 is 1. Let's see, how do I show you that? If I have 3 to the fourth power, that's really 3 times 3 times 3 times 3 times 1. 3 to the third power, I'm undoing that, and that is 3 times 3 times 3 times 1. If I take another one away from the exponent, so I have 3 squared, that means I have 3 times 3 times 1. If I take another one away from the exponent, so I have 3 to the first, that's 3 times 1. If I take another one away from the exponent, so I have 3 to the 0, that equals that 1. So as I'm subtracting from the exponents, what I'm doing each time is I'm crossing out a 3, leaving just 1. Now if I take another one away from the exponent, that gives me 3 to the 1, and what I'm doing each time is, as I'm crossing out, what I'm really doing is dividing by 3, and so that becomes 1/3. And if I take another one away, that gives me 1 to the I divide by another 3, or I'm now dividing by 3 squared. So as I'm subtracting exponents, I'm really dividing out a 3 each time. And as I keep going negative, I'm dividing out a 3, or I'm dividing by another 3. So this negative on the exponent doesn't say it's a negative. It's the value is not negative. It's saying do the opposite of multiply. So if I have a to the negative n, I just take that term and I put it in the denominator, unless of course it's already there. If I have 1 over a to the negative n, I'm doing the opposite of this. So what I'm doing then is I bring it up to the numerator position and drop the negative. Um, this is a division, and so I, just like when I multiplied up here, I added the exponents. This is division, so I subtract the exponents. And this is a power of a power, or power to a power. I multiply the exponents. Because if I have a squared cubed, I have 3 sets of a squared. So that's a times a times a times a times a times a, which gives me 3 times 2. Because it's a power of a fraction or a division problem, what I can do is I can take that and give the exponent to both the numerator and the denominator. Here is that's power of a quotient. Here's power of a product. So I can just give that to both of them. So a times b to the n power is a to the m times b to the m. And when it's a negative exponent and I have a quotient there, what I can do to get rid of the negative on the exponent is I can just invert the quotient. So a negative 3, not a negative 3 halves. 3 halves to the negative fourth becomes a 2/4 to the positive fourth. So negative x in parentheses to the negative second power is not equal to negative x to the negative 2. Well, what this one, applying the exponent rules to, what I get is 1 over negative x squared, and that means that that will be 1 over x squared, because a negative to a second power makes it positive, and that is not the same as this, because that means I'm just putting this downstairs, x squared, and it's still negative. So this square undoes that negative, but this square has nothing to do with that negative because it's not glued to a parentheses. Here what I have is, since it is the same, because it's a negative, that becomes negative x to the third, and this is still a negative x to the third. That's when I get rid of the exponents. And a negative to the third power is still a negative, so that's why this still is true. This actually is a times b to the negative 1. The negative, the exponent, you have to take care of the exponent before you take care of the multiplication, so the exponent only belongs to the b. So that really is a to b, and that's not the same as 1 over a to the b, because because of the product raised, you give it to both of them, and so they would go down, and so no, that's not true. Let's see. What we have here is we have a to the negative 2 to the negative 1. Remember, I can distribute that out times b to the negative 2 times to the negative 1, and then a power to a power. Negative times a negative makes a squared. Negative times negative makes b squared. And so, yes, that is true. And because of this plus, I can't distribute that out. So this is 1 over a squared plus 1 over b squared, all raised to the negative 1. And so that becomes 1 over a squared plus 1 over b squared. And that's not the same as a squared plus b squared. Write each of the following in simplest form using positive exponents in the final answer. Well, I know that this is 2 times 8 squared. I can split that out times 8 to the negative third. I know that I can then give that, so that's 2 squared times 8 squared times 8 to the negative third, and then I can say I can add those, so that becomes 2 squared times 8, which equals 4 times 8, which is 32. Oh, using positive exponents in the final answer. And 2 times 2 is 4 times 2 is 8, 1632, so I know that's 2 to the 5th. There's a positive exponent. There's 2 of them, there's 3 of them there, 2 times 2 and 2 times 2 times 2, so that gives me 2 to the 5th. How can I chop this up? I know that this is 4 times 5 squared divided by 2 to the 4th. I know that 4 is 2 squared times 5 to there divided by 2 to the 4th. So that's 2 to the 4th times 5 squared divided by 2 to the 4th. Those can undo each other because 2 to the 4th divided by 2 to the 4th. Subtract the exponents, so I know that I just have 5 squared. Well, that's 1/10 plus 5 times 1/100th plus 3 times 1/1000ths, and so that's 1/10 plus 5 hundredths plus 3 1,000ths, which makes 153 1,000ths, because if I multiply this by 2 to get there and that there, so I have common denominators. I have 153 1,000ths times 10 to the third, which is 1,000. So I have 153 1,000ths times 1,000 over 1, and they undo each other. I have 153. And this is x cubed over y squared raised to the negative 4th power. So that means I can flip it and get y squared over x cubed to the 4th power, and then it's a quotient, so I can give that there. So that's y to the 8th, and that's x to the 12th. A ratio is used to compare quantities, ratio of A to B, miles to hour, whatever. It's usually written as A to B or A to the B. It's a part to a part or part to a whole or whole to a part comparisons. There are 7 males and 12 females in the Dewdrop Inn on Monday evening. In the game room next door, 14 males and 24 females. So express the number of males to females at the inn as a ratio. So you have 7 males to 12 females. It's part to part because it's not to the whole. It's not to all people or whatever. And in the game room, it's 14 to 24 or 7 to 12. And express the number of males in the game room to the number of people in the game room. There are a total of 14 and 24 makes a total of 38 people, and there are 14 males, so 14 to 38 or 7 to 9. A proportion is a statement that two given ratios are equal. And so if you have one ratio and you have another ratio and you set them equal, they're saying that if you reduce them or whatever, they're the same value. Ali and Bente typed at the same speed. Ali started typing first when Ali had typed 8 pages. Bente had typed 4 pages. When Bente had typed 10 pages, how many had Ali? So we have A to B. And so when Ali had typed 8, Bente had typed 4. Since they are at the same speed, we know it will be equal. When Bente had typed 10, how many had Ali typed? And since Bente had typed an additional 6 pages, since they're typing at the same speed, you can just add 6 or 14. So I guess you don't have to do the proportion at all. Carl can type 8 pages for every 4 pages that Dan can type. So every time Dan types 4 pages, Carl types 8. If Dan has typed 12 pages, Dan types twice as many, so that would be 24, because we have 8 for Carl and 4 for Dan, and so that'd be 4, 8, that'd be 16, and 12 would be 24. So you see that Carl is 2 times Dan. If there are 3 cars for every 8 students at a high school, how many cars are there for 1,200 students? So we have 3 cars for every 8 students, and there are 1,200 students. We need to know the value of x. This is where we do cross multiplication, cross products, just to find a quick value for x. We could find a common denominator and just compare them and things, but we take this 1200 and we take this 8. So we have 3 times 1200 is equal to 8 times x. 3600 is divided by, and then we isolate the x by dividing both sides and find out that there are 450 cars. The constant of proportionality. This really is just the slope in a direct variation. So the linear equation, the line will go through the origin, through the origin, and the k is just the slope. We call that the constant of proportionality. It tends to confuse students. The book that we're currently adopting now does use the slope instead of the constant of proportionality, just to say that it's slope, so that we're not getting the students confused, and it's how tippy the line is. Cross multiplication method. Instruction in solving proportions should include methods that have a strong intuitive basis. The so-called cross multiplication method can be developed meaningfully if it arises naturally from students' work. That's where we had 3 to 800 is equal to x, or 3 to 8 or whatever is equal to that. Those kind of things, and we solved it by doing cross products. This isn't, it's an algorithm that works. It's fast, it's simple. It can be confusing for students and leaving them with a misunderstanding of where the answer comes from. They get an answer, but it's an answer that's nonsensical. Other approaches to solving proportions are often more intuitive and quite powerful. For example, when trying to decide which is better to buy 12 tickets for $15 or 20 tickets for $23, it's probably better to find out how much one ticket costs, and then we can compare under each version, and then we can compare and find out which is the better deal. A little more intuitive understanding of what the problem is all about is to find the unit, and this is called finding the unit price of each ticket, and then we can do a direct comparison. So use the scaling strategy to determine which is better buy 12 for 15 or 20 for 23. The scaling strategy for solving the problem would involve finding the cost for a common number of tickets, the least common multiple. So now they're going to find, they say the common multiple of 12 and 20 is 60. You can find that by saying 12 breaks down to 3 times 4, which is 2 times 2. So 12 is 2 times 2 times 3, and 20 is 2 times 10 and 2 times 5. So 20 is 2 times 2 times 5. We have to have a 5 there and a 3 there. 5 times, so this will be our common denominator here, our common value of 60. So then we want to say, okay, 12 tickets for $15. So we multiply the 15 by 5 and get 75. And we multiply the 23 by 3 and get 69. We find out that that's the better deal. Use the unit rate, and now we're going, instead of finding least common multiple, we're finding how much for one ticket. And so 12 tickets for $15. That means we have 15 divided by 12 to find out how much by, or 12 divided by 15. Oh no, 15 divided by 12 to find out how much for one ticket is $1.25, and we want to find out how many 23 tickets cost. That's $1.15. We can still see that it's the better buy because now we are comparing a direct comparison on the same number of tickets. You can read this on your own, so if you pause it now. Proportion for any rational numbers a and b and c and d. A over b is equal to c over d if and only if the reciprocals are also b over a is the same as d over c if the reciprocals are the same. For any rational numbers a, b, and c, d, if AC, a divided by c is equal to b divided by d, and you get that because we're finding common denominators and dividing things out. Scale drawings. Ratio and proportion are used in scale drawings. For example, the old days when we had paper maps, it wouldn't do much good to have a map that's full scale. So we want to shrink it down. Kids making model cars, it's not very effective to make a plastic model car that's full size, so they scale it down, and everything is scaled down at the same rate. That's what a scale drawing is all about. So the floor plan of the main floor of a house, and the figure is drawn to a scale of 1 to 300. So that means 300 feet is in real life is equal to 1 foot on the drawing, or inches. 300 inches in real life is equal to 1 inch on the drawing, or meters or centimeters or whatever. So here they're saying that 1 centimeter in the drawing is in real life 300 centimeters, and so a construction worker can measure that that's 2.5 centimeters, multiply it by a scale factor of 300, and find out how long it really is.